If you throw a tennis ball against a solid brick wall, the rules are very simple. The ball hits the bricks and bounces right back, every single time. But scientists have spent decades arguing over whether those same rules apply when things get very, very small. Imagine shrinking that scenario down until the ball is a single subatomic particle, and the wall is as thin as a soap bubble. If you throw that tiny particle against that thin wall, something impossible happens. There is a small chance it won't bounce. Instead, it simply appears on the other side. It doesn't break the wall, and it doesn't sneak around the edges. It passes straight through solid matter, as if the wall wasn't even there. This ghost-like behavior is a proven foundational rule of the microscopic universe. But we didn't know if this was a trick only individual particles could pull off, or if it worked for larger objects too.
To understand how a solid object ghosts through a wall, you have to stop thinking of particles as tiny marbles. It's more accurate to see them as a blurry cloud of fog. This cloud is what we call a probability wave. It's brightest at the center, which is where the particle is most likely to be, but the edges fade out into a faint, see-through mist. Because those misty edges fade but never quite reach zero, there is always a tiny mathematical chance that the particle is actually located far away from its center. At this scale, objects are not solid points. They are instead overlapping fields of maybe, and that maybe is exactly what allows them to move through obstacles. When this maybe cloud hits a thin barrier, most of it bounces back, but because the cloud is fuzzy, a sliver of mist reaches through the wall. Since a piece already exists past the barrier, the entire particle instantly teleports to that spot. This process of ghosting through a barrier is called quantum tunneling. We already see this in our pockets. Components in modern phone chips are now so small and close together that engineers have to fight to keep electrons from tunneling across gaps where they don't belong. We watched individual particles do this for years, but the big question remained: could a massive group of particles, something large enough for us to see and hold, tunnel through a wall together? That brings us to the 2025 Nobel Prize winners, John Clark, Michel Dvoret, and John Martinez. They set out to prove that this ghosting wasn't just for tiny, lonely particles. It could happen to objects in our world, too. They built a special gate called a Josephson junction, two superconducting wires separated by a thin, insulating wall that no normal electron should ever be able to cross. Usually, getting billions of electrons to work together is like herding cats. They are all negatively charged, so they constantly push each other away and bounce around randomly, losing their focus. To get them to cooperate, the team had to remove all the heat that causes that random bouncing. They cooled their experiment down until it was colder than the deepest reaches of outer space. In this extreme cold, all normal motion stops. This is the only environment where billions of particles can finally settle down and link up. Instead of fighting and pushing each other away, the electrons start to pair up. They begin to move in perfect synchronization, like a well-drilled team. Inside the wire, billions of these pairs stop acting like individuals. They merge their maybe clouds together to form one massive wave that moves in perfect unison. The researchers then pushed this massive wave of particles toward the insulating wall. The wall no longer blocked a single speck. It faced a giant unified object of billions of particles. As the team increased power, they saw it. The whole group jumped. Billions of electrons tunneled through the wall simultaneously, appearing on the other side intact. Because the system was cold, there was no heat energy to push them over the wall. This proved the jump was a pure quantum magic trick, happening at a scale we can actually measure. This discovery settled the great debate. The weirdness of the quantum world doesn't vanish when things get bigger. It's a fundamental part of our universe. But more importantly, it gave us a way to build a new kind of computer. By proving we can force a massive group of particles to jump across a gap on command, we gained a way to switch quantum states on and off. Controlling that jump is the core of how a quantum computer's memory, or qubit, works. Without this discovery, we couldn't build the hardware you see here. By proving that a wave of matter can ghost through a wall, these scientists didn't just win a prize, they unlocked the control system for the next era of human technology.